Good morning to everybody. Welcome to the third workshop on methodologies for official statistics. As that I have the honor to introduce, being the coordinator of the advisory board on methodological issues in Istat. I think that the best welcome can be offered to you by the two heads of the departments, the heads of the two departments of the National Statistical Institute, mainly Monica Pratesi, the head of the Department of Statistical Production, and Massimo Fedeli, head of the Department for Development of Methods and Technology for Production and Dissemination of Statistical Information. We have a very dense program in 2 days with 4 sessions, and before each session, we will have a very important event that is a master class given by, I think, people that are among the best researchers on the different topics. And so I think that the junction between the topics of the master class and the topics of all the invited talks that have been prepared by participants and which will, I hope, can be followed by a very passionate discussion from the floor and also from the people that are in their offices, and they are really welcome to this conference because it is held in the mixed mode. One part is in present, but another part of people, for us very, very important, are in their offices, in their desk, in their towns, and we really hope that the common discussion can be very, very fruitful for each of us. If you allow me, I may say that the floor is first to Monica Pratesi.
So good morning, very welcome for those of you in person and to the online person for this event. It is important to say as a first thing that the Istat is adopting a multi-source approach in statistical production. This means that we are aligning with the increasing complexity and richness of the information ecosystem, aiming to meet the demands of a rapidly evolving society. In this age, my personal idea, and I think that this is shared with my colleagues, is that in the age of big data and digital transformation, still household surveys are increasingly serving as a key example of collaborative statistics. They are here to integrate diverse data sources, including citizen-generated data, and can deliver richer, more comprehensive insights addressing critical challenges in inclusivity, efficiency, and relevance. Integrating household survey data with external sources enhances its utility and value. We have to integrate administrative data, linking population registers, health records, or tax data. And this will enrich the analysis while at the same time reducing respondent burden. Integrating also geospatial data, and this is to combine survey responses with the satellite imagery and geographic information systems, and also big data, incorporating call detail records, social media activity, and sensor data. This integration creates a multidimensional view of societal trends, enabling a deeper understanding of complex issues. And in this, citizen-generated data produced actively or passively by individuals offers a unique opportunity to enhance household surveys and the whole data ecosystem. This obviously offers advantages, but also challenges and the need of mitigation strategies. We have to invest in data privacy and ethics, in data quality and harmonization, to enhance equity in participation and trust and collaboration. And this requires also, and this is why we are here for this workshop in methodology, the development of new methods. Non-probability sampling has a key role in this, and new data quality principles, especially when we are including new data sources based on artificial intelligence. And also we need new methods to analyze these multi-source data sets as small area estimation. So, looking at the future, as household surveys and the other data sources evolve into a collaborative statistics framework, I envision that the future will be characterized by a hybrid data ecosystem, systems maybe, where we integrate household surveys, administrative data, and citizen-generated data for comprehensive analysis. And we will adopt a citizen-centric approach, actively involving citizens in all the stages of data life cycle, from design to dissemination. Technological advancements are here to stay as well, so we need to leverage artificial intelligence, blockchain, and advanced analytics to ensure secure, efficient, and meaningful data integration. So household surveys are here to stay and are a key element in this multi-source approach, enriched by data integration, citizen contributions. This fruitful use of household survey data and citizen data will allow a data-driven collaboration, ensuring that statistics serve as a cornerstone for equitable and sustainable development. So this is what I think it is important to say, just as an introduction to what Massimo Fedeli is explaining you. Thank you.
Thank you, Monica. It's very pleasure for me to introduce this workshop. I want to speak about a few very critical topics for us because in landscape official statistics is undergoing a profound transformation driven by the need to adapt to a rapidly changing world. Traditional statistical approach, while fundamental, are increasingly challenged by evolving societal demands, technological advancement, and complexity of modern data ecosystem. In response, the National Statistical Institute are embracing innovating strategy and integrating diverse data sources, as said before, to ensure the relevance, efficiency, and accuracy of their outputs. In fact, greater investment are being dedicated to research and development of multi-source statistics production to face the ongoing decline in survey response rate and the high costs associated with large-scale survey. Identifying new data source and determining new integrated them into the statistical procedure of National Statistical Institute are key challenges in the field of multi-source integrated statistics research. Traditionally, this source has primarily consisted of administrative data, but in the last decade, increasing attention has been dedicated toward to big data and other non-probability data source. As NOV developed extensive expertise, Istat has developed extensive expertise in the integrated use of diverse data source for the production and multidimensional official statistics. Since 2060, Istat has adopted the new statistical production strategies based on multi-source approach that combine survey data with large-scale administrative source. This shift has required methodological, technological, and organizational innovation alongside extensive research, leading to a progressive transformation of statistical production processes. Traditional procedure for generating multi-source statistics required substantial revisions. Enhancement in record linkage and data integration method are essential for effectively combining diverse sources. Moreover, standard methodologies such as estimation, calibration, and measurement error accounting must be adapted for use in this context. A cornerstone of Istat new strategies is the integrated system or register, which serve as the backbone of production framework. The integrated system register is built on record level, primarily through the massive integration of administrative data, supplemented by survey data, where administrative data source lack coverage in the subpopulation of interest. These processes involve record linkage, editing, and imputation techniques. In the field of socioeconomic statistics, Istat has developed several registers, including the population register, labor register, disability register, and income register. Similar framework are being developed for enterprise with tool like in enterprise frame and frame register for agriculture sector. Territorial data is managed through the register of place, which include the detailed information on address, geolocalization, and administrative units. Other major milestone in the development of multi-source processes is the evolution of the permanent census of population and housing. In 2012, it has been introduced for the first time in Italian legislation, the new population census, while 2018 it has abandoned the traditional decennial door-to-door enumerate with the implementation of a combined approach to integrate administrative data and sample survey information. The strategy underlying the new population census system is based on the development of an innovative methodology to integrate the information stored into register with data specifically collected through a specific sample survey called the census master sample. All this methodological activity must be supported by many other actions, which Istat has increasingly prioritized in recent years. For example, data integration practitioners often highlight that the majority of their time is spent not on applying statistical method, but on checking metadata and understanding and harmonization its context. Metadata harmonization, therefore, emerges as a critical objective for improving efficiency. Istat is actively working on metadata harmonization, both internal and external, with various collaboration. Internally, Istat is developing a new metadata system designed to promote the consistent use of common glossary across various data production processes. This new metadata system will also document the provenance of concept, providing clear explanation of the input data required for calculating indicator and detailing new how these input data were actually transformed. Externally, Istat has taken on the role of metadata steward, supporting public administration in making their administrative procedure interoperability. This approach has a significant impact on official statistics as administrative procedure, generated archive, and are incorporated into commonly used statistical registers. Among the public administration currently involved in this project, we can see it is Italian National Institute of Social Security and Ministry of Economy and Finance. In the near future, research and study of the use of the non-traditional data sources, such as big data, should be further developed. I am pleased to see that this is one of the main topics of this workshop. Istat is already engaged in various initiatives, including the established use of scanner data for price estimation, a recent application Twitter data for sentiment analysis on the economy and violence against women, as well as experiments with smart survey in the household budget survey and time use survey. However, the new Istat standard and technologies are essential for producing statistics for multiple data sources, supporting the integrated ecosystem that can enable integrated analysis from all available data sources. Research on this field has also advanced the application of AI and the machine learning techniques in the creation of official statistic use news data sources, including big data. Finally, as official statistics increasingly rely on the integration of survey data with non-probability data sources such as administrative and big data, new criteria or the standards are necessary to accurately measure and communicate their quality to stakeholders and policymakers. Istat is already making significant investment in this area, with notable progress in integrated use of administrative data. Research is also underway to develop a new quality evaluating framework for the use of big data in socioeconomics analysis. Personally, I actively promote and encourage collaboration in this matter among all researchers in my department, with academic institutions and other research institutes, both in Italy and abroad. Thank you. Thank you.
I thank you very much to both introducers, and let me illustrate a little bit more the structure of the conference. Indeed, what will be a peculiarity of the conference is the strict respect of timing. Because there are people that are connected online, and to have their full collaboration is really for us a very, very, very important thing. And I insist on the fact that the people that participate to this conference online really is really welcome, and for us the situation is really like if they were here with us. This is very important, and it is very important also that they do participate in the discussion. As I mentioned it before, we have 4 sessions. Each session has a master class, a nice conference presented by illustrious statisticians that comes from all over the world, and then we will have a discussion is welcome after each masterclass, there is a first session on methods for multi-source statistics, and then there is a session for methods for non-probabilistic data sources today. Tomorrow, we will have a session on data science, and official statistics. And then session 4, new data sources for small area estimation, is organized in collaboration with the International Association of Survey Statisticians. This is very important, and this is a witness of the fact that the methodological work of Istat is not invented. It does not come from nothing. It means that there is a strict collaboration with the main scientific societies on the topic. This is really very, very, very important, and for this we have, and moreover, we have the president of the International Association of Survey Statisticians that is a member of the advisory board, Natalie, Professor Shlomo, she's a member of the advisory board on methodologies in statistics in the Istat. And indeed, the production, of course, of data, of figures for our country is very, very important. This is the main duty of the Institute, but indeed the work that is done is also of high scientific quality, and this is very, very important. And the witness of this is exactly this our conferences like this one, and this is really very, very, very important. And we trust that let's say the example that is given by these conferences can be really something important also for the people of the Institute that do not directly participate to the methodological advancement. But the point is that people are not doing things only for tradition. There is always the wish for innovation, and there is always the wish of helping the country to publish and to offer to citizens what is at the moment the best of what can be produced by official statistics. This is really very, very important, and really we wish that there is a kind of stimulus and of reciprocal interaction on this point. And for us, we of the methodology, the advisory committee on methodological affairs, we are not stupid scientists that are speaking here and there of useless things. We try to understand what can be useful. And I hope that everybody can trust. We try to do our best. Well, it occurs that sometimes we are lost in strange things, but it's not our habit. We try to follow and to give suggestions for practical things. The idea is that the citizen needs to have figures, and moreover, in different countries, the figures have more or less to be comparable. And for us, this is really, really something that is very, very, very important. So really, for us is really a pleasure to begin with conference. And if you're right, we invite the chair of the first masterclass, Professor Alfo, that will introduce and will be the chair of the first important masterclass held by Professor Pfefferman. Thank you very much to everybody, and we begin in time.
Good morning to everyone. Thank you very much for joining us. It's a huge pleasure for me to introduce Professor Danny Pfefferman from the University of Southampton. He's professor of social statistics there. He's a member of the Southampton Social Science Research Institute, which is one of the largest group of statisticians in the whole UK. Is Professor Emeritus at the Hebrew University of Jerusalem in Israel, has been before the national statistician and the Director General of the Israel Central Bureau of Statistics. And more importantly, has been working on several very interesting fields during the past few years. Has been is producing a lot of scientific papers in leading scientific journals, covering analytic inference in complex sample surveys, small area prediction, small area estimation, and in particular for me, as I've been an interested reader of his contribution for handling informative sampling and informative no response in surveys, but not only in surveys, also in complex statistical models. I remember a paper on non-ignorable missing response, or maybe non-ignorable sampling design in multi-level models. He co-authored also the famous book on sampling surveys, and has been before the president of the International Association of Survey Statisticians, and has been a member of the International Statistical Institute, the American Statistical Association, and International Mathematical Institute. So it's a huge pleasure for me to introduce him and let him the floor for giving us the masterclass on methods for multi-source statistics. Thank you very much, Professor.
Thank you very much for the nice introduction. And thanks for inviting me. It's a great pleasure to be here. I'm afraid my presentation will have quite a few equations, which is not very kind for an opening presentation of a conference, but all those equations are actually very simple, so you shouldn't have any problems following. It's a joint article with Daniela Marella and Donato Suma, which you all know. They are from here. So let me start. Tighten budgets. Tighten budget and constant decrease in response rate in traditional surveys has stimulated research into the use of non-probability sample data, such as administrative record, voluntary internet surveys, and other kinds of non-probability samples. A major concern with the use of this kind of data is their non-representativeness due to possible selection bias, which, if not accounted for, may bias the inference. By the way, I know the 20 minutes or something after my talk for questions and comments, but if you have any question during my talk, don't hesitate. So what is official statistics? Why is it important? Publication by national statistical offices, NSO, based on a survey, census, administrative data, big data. Official statistics is what people hear of almost daily: unemployment rates, price indexes, poverty measures, house prices, establishment statistics, health and environmental statistics, etc., etc. For most people, official statistics is what statistics is all about. Official statistics is what policymakers use, or better to say, should use for planning and decisions. Growing demands for detailed, timely data, huge technological developments, declining response rates, heightened budgets. So all those make the use of sort of non-probability samples more and more important. So anyway, we face big new challenges. So here just sort of the main methods of data collection for official statistics, surveys, that we're all familiar with, based on probability samples. I feel that it's still the most common and in many ways the most reliable method. Administrative records often requires linking several big files, which can be problematic and actually increase privacy concerns. Censuses, non-probability samples, as far as I can tell, it's not yet really implemented routinely for official statistics, but there is an increased pressure on national statistical offices all over the world to digitize, modernize their data sources, and basically combinations of all or some of the methods above. So what's the main issue in the use of non-probability samples? Non-representativeness, that's a major concern in the use of non-probability data for official statistics. House sales are advertised on the internet do not represent properly all house sales. Web scraping for job vacancies does not represent all job vacancies. Social media, not representative of the general public. No problem when the non-probability data serve as predictors of other variables. There are some famous examples, like the use of the billion price project to predict the consumer price index in the US, job adverts to predict employment or job vacancies. I think this is applied routinely in Australia, satellite images to predict crops, etc., etc. It requires proper statistical analysis to identify and test routinely the prediction models. So how do we account or possibly account for the non-representativeness of the big data? So as I said, this is a major concern. Method considered in the literature to deal with these non-probability samples can be divided into two classes. Integration of non-probability sample with an appropriate probability sample, or trying to make the inference based only on the non-probability sample, so no data integration. Is everything clear so far? No equation yet. So here is the general framework that I will consider in this presentation. A large non-probability sample, S&P, with observations on variable Y and X is available, but this sample is possibly affected by selection bias. An informative probability sample, SPS, possibly subjected to not missing at random non-response, may also be available, but this sample only contains observations on X. The aim is to estimate the joint probability distribution function of the variables X and Y, either because this is the purpose on itself, or as an intermediate step for estimating population totals of Y values in the population. Consider alternative methods for integrating the data available in the two samples, and we also consider the case where only data from the non-probability sample is available. So suppose that the non-probability sample, and the probability samples have no units in common. I will remark towards the end of my talk on this assumption. Following, we apply the empirical likelihood approach, under which the population distribution is approximated by a multinomial distribution which supports given by the empirical observations in the two samples. The aim is to estimate, as I said, the joint probability that x equals xi, y equals yi of the multinomial distribution, and to estimate of the population total of y. Let me denote by pix the probability that x equals xi, the population probability of x. So now we start with some equations. Let IPS be the sample indicator. So it takes the value 1 if population unit I is drawn to the sample, 0 otherwise. Then for unit I in probability sample, what is the sample probability of x? If you just use Bayes formula, basically what I'm asking is, what's the probability of xi given that the unit is in the sample? So by Bayes, theorem, it's just the probability of being in the sample given x times the population probability pix. Just divide just by the, if you want, the integral of the numerator, just the probability, unconditional probability on x. So this is what defines informative sampling. Notice that the probability for the sample unit is the same as the population probability if the probability of IPS equals 1 given xi is not depending on xi. Then the numerator and the denominator cancel out. Next, suppose that the probability sample is also subject to not missing at random or n-Marnan response, which I define in a second. So here again, let me define the response indicator RIPS, which is 1 or 0, depending on whether sampled unit I responds or doesn't respond. Now just denote by RPS the set of the responding units. So we sample a sample PS, but we end up with the set RPS, which are all those units actually respond. The response process is assumed to be independent between units. So now let's ask for a unit I that is in the sample and response. What is the probability of unit I to have the value xi? So it's P of xi. Get used to this. So it's the probability of I. This is what I want to say. So it's the probability of responding given that the unit is in the sample nxi divided by the probability to respond given that the unit is in the sample times the probability under complete response, what we saw before. And if you plug in the previous expression for PI XPS, you end up with this. So what is the probability of PI RPSX? It's a function of the corresponding population probability, the conditional probability of selection to the sample, and the response probability P of RIS even 1 or 0 given xi and that the unit is in the sample. So here again, unless the probability to respond given xi and IPS equals 1 is the same as the probability given just that the unit is in the sample, the probability of I RPS X, which we have here in the this probability that I just wrote the expression, is different because of not missing at random non-response from the sample probability, which under informative sampling is different from the population probability. And what we clearly want to estimate is the population probability. So how can we estimate the sampling and response probabilities? Let's first consider the sampling probabilities. The probability of being in the sample given xi, you can actually write it as 1 over the expected value of the corresponding sampling weight given xi. This is an equation that been established already in 1999. So WIPS is just the sampling weight or in the sample SPS. So if we can assume that the response is independent of the sample selection, we can actually estimate the expected value of the sampling weights given xi for the responding unit, so for the sampling units based on the responding units. So we can then, using this equation here, we can then estimate the probability of being in the sample given xi simply by regressing WIPS against xi using the observed data that we have. So we don't have to, I'll write to you in a minute the likelihood equation, but those probabilities we can estimate outside the likelihood. However, for the response probability, we don't have any sampling weights, so we don't know what those probabilities are. So we need to postulate a parametric model, say logistic, and just wrote it down there. So just some function, say logistic, is all defining the model parameters. So in the likelihood, so in a minute, we will have to estimate also those coefficients. So let me denote by RPSI. It's all the x's for which xk equals xi, so that the probabilities are the same. For this probability is the same for all k in R. And RPS is just the union of all those RPSI. So if I have 6 x's that are all the same for 6 different units, I can just consider them or denoted by RPSI. So what is the empirical respondent's likelihood? Again, based only on the responding units, just the product under independent of all those probabilities. And here I just wrote to you the expressions that we had before. So I said this depends only on the units that you actually observe. And the unknown parameters are the population probabilities PIX here and the response parameters rho. And as I said before, this probability, the probability to be selected to the sample given X, are estimated outside the likelihood. So I hope you notice that so far I only considered the probability sample and showed what is my likelihood, empirical likelihood based on the observed data for the responding units. Now let me consider the non-probability sample. So in SNP, we observe X and Y, but it may be subject to informative selection, depending on both variables. So I consider the case where the probability to be a non-probability sample may depend not just on X, but also on Y. So similarly to what I showed before, let I and P be the sample indicator to the non-probability sample. So we again apply the empirical likelihood to approximate the population probabilities, this time of X and Y, by multinomial model with probabilities. Just a notation. So here again, what are the sample probabilities in the non-probability sample? Again, just by use of Bayes' theorem, the probability of xi, given that a unit is in the non-probability sample, which is the probability to be in the non-probability sample, given x and y, divided by just by the marginal probability, times the true population joint probability. So this is informative selection. And what I have in the denominator, that's the function of or the sum of the probabilities in the numerator. Here again, I don't have, for the non-probability sample, I don't have any sampling weights or anything. So again, I have to model those probabilities. As I said before, I can test the models that I use. So the probabilities are modeled parametrically. Again, I can use the logistic, broadly, more complicated functions denoted by H, the function of the model that I use, and gamma are defining the model parameters. So what is the empirical sample likelihood based only on the non-probability sample? It's just the product of those probabilities. We assume, as I said before, no common units in the two samples. So the empirical likelihood based on the data in the probability sample and the data in the non-probability sample is just the product of the two likelihoods which I've written there. What are the unknown parameters again? It's the marginal probability of X, the joint probability of XY, and the sampling parameters gamma, and the response parameters rho, in those two functions that I have to model those probability. The likelihood is maximized subject to the constraints. Obviously, the probabilities have to be positive. Sum is 1. The summation of the different values of xi in the response set and the different values of xi, yi in the non-probability sample. The estimation can be and should further enhanced by adding calibration constraints. In particular, if the population size and or the population mean of the excess, or some of the excess are known, we can add this kind of calibration constraints. So the constraint in the left-hand side just tells you that the PI are those empirical likelihood probabilities or mass functions, mass probabilities. So it just tells you that it should give you the right mean of the excess. The upper constraint is sort of a constraint on the gamma coefficients. And the lower constraint is actually a constraint on the rho coefficients. The point is that the probabilities, the marginal probabilities of the X values can actually be estimated also from the non-probability sample. So far, I only consider the estimation of the joint probabilities, but once you have estimates of the joint probabilities, you can easily get estimates of the marginal probabilities. So we now have two sets of estimates of those probabilities which can be harmonized. Use a linear combination of the two probabilities. A plausible choice of this coefficient in this combination is just the sample sizes, they're proportional to the sample size. This article with Daniela Marella, we consider other harmonization possibilities. One way, by the way, is add lambda to the unknown parameters. So our final estimate of lambda, the final integrated estimate of the joint probability is just the expression that I wrote there. So you can see the logic of this estimator. Just the joint divided by the marginal. Now suppose I want to estimate the totals of the y values. Here are two possibilities. One is just to use the usually call it using those PIs. Just this will just the sum will give you an estimator of the mean, so multiplied by n if n is known. The other one is to use this sort of classical survey estimator using those probabilities, the sampling probabilities to the non-probability sample as my sampling weight, sort of sampling weight. Is that all clear? Here are some further remarks. If some of the, so far I assume that the units in the probability sample, there are no common units in the probability sample and the non-probability sample. But if some of the units in the probability sample are also included in the non-probability sample, then I have a unique identifier. We can apply the proposed approach to the units that are in the probability sample and not included in the non-probability. Because for those that are included in both samples, I know the y and the x's. And so need to modify the sampling weights in the probability sample in this case. We considered integration of the data in the probability and non-probability samples, but actually I showed you 3-4 slides ago how the probabilities, those joint probabilities, and hence the population total, can be estimated only from the non-probability. Integration, if you have a sample to integrate with. Yeah, Jan.
Thank you. Concerning the first remark, if the probability sample would be a register, so you have a complete enumeration, can you also use that kind of auxiliary information just for countries like the Netherlands?
Yeah, just.
Did you all hear the question? If the probability sample is a register, then it's not a probability sample. So basically what you are asking is how to integrate two non-probability samples. Along the same ways, only I have to now distinguish, instead of considering non-response, etc., I have to follow the same steps as before for this register data. Yeah, so I said already the second remark, the proposed approach does not require knowledge of the X values for all population units, but it does assume knowledge of some of their means for the calibration constraints. That's important. The inclusion probabilities and the response probabilities might actually depend on other variables rather than y and x. So they might depend on some z variables. But you only need to model them as a function of x and y, as long as the model of y given x. So if you follow the steps that show with Bayes' theorem, etc., I only need to model everything as a function of y and x. The proposed approach is model dependent, because remember, I assume the model for the response probabilities and for the selection probabilities, but the models can actually be tested using classical test statistics. Illustrate this later. The likelihoods considered, how we actually maximize the likelihood is the calibration constraint. We maximize by application of the profile likelihood, this function in R, which we have used successfully. So let me just consider 2 or 3 other approaches that have been proposed in the literature for data integration. Revere proposed to deal with the selection bias of a non-probability sample by use of sample matching. Their approach consists of using a probability sample as a reference sample from the target that is drawn from the target population with some known probabilities pi I, and then matching for every unit in the probability sample an element k from the non-probability sample, which is the closest to xi by some metric, say the Euclidean metric or any other metric. This defines a matched probability sample Sm, because I just match to every unit that has been selected for the probability sample some data from the non-probability sample with observations xi, y tilde I, where y tilde I is the y value of the matched element from the non-probability sample. Now you have a probability sample with observation y and x, then you can just use classical sampling methods for estimation of whatever you are interested in. Instead of matching one record, one can actually match k records, k nearest records, and then you can select at random the matched record out of them. This is known as the k nearest neighbors, and I know some people from Italy have worked on this as well. Tim and Wang, Tim is here with us, proposed the following procedure to correct for the selection bias of in the non-probability sample. Assumption, membership of the probability sample elements in the non-probability sample are known. So you know for every unit in the probability sample where it is contained also in the non-probability sample. So let me denote by delta I, 1, 0, if I is in the non-probability sample or not. So our probability sample data contain the x's and the delta I. So the proposed procedure model this probability. Qi is the probability of delta I equals 1. So the probability the unit will be in the non-probability sample using the data in the probability sample. So you get an estimator. And then there are at least 2 possibilities to estimate a population total. Again, the left-hand side is just sort of the classical survey estimator, sum of Wi, Yi, but Wi are now the 1 over the estimated probability to be in the sample. And kind of ways and multiply by Kapp and Brewer and Hayek estimator. So those 2 approaches are suitable as long as the selection to the non-probability sample is sort of missing at random. In other words, it depends on X, but not on Y. And this is important. So if you can verify that it depends only on X, the selection to the non-probability sample, then these are good good procedures. And also, at least in what all the sample is assumed to be fully observed, so non-response. What happens if the sample may depend actually on why the sample selection? So in a recent article, Kim and Morikawa, they combine a non-ignorable informative sample selection model with the empirical likelihood approach. So again, let delta I be the sample indicator, and notice now the probability to be in the non-probability sample is allowed to depend on Y and not just on X. The auxiliary variables Xi are assumed to be known for all the units in the population. So here are just the empirical likelihood equation that they use. And again, they have constraints. The second constraint, they call it a bias calibration constraint, where the third set of constraints is in order to improve the efficiency of the empirical likelihood estimate. In practice, the sample selection probabilities are unknown, and out of again, they assume a parametric model and estimate those probabilities, but they are able to estimate it outside the likelihood. And here again, the estimation of the population totals. You can either use this classical survey estimate or just use those empirical likelihood probabilities. This is a novel approach for estimating fine population parameters from a non-probability sample subject to non-ignorable selection probabilities, but the assumption that the Xi are known for every unit in the population, at least from my experience, is quite restricted. I mean, it may be the case for inferences, etc., that are done within the NSO because they know all the X's, but not for analysts. They will not usually provide this information for analysts outside the bureau. Okay, so I'll show you now some simulation results, and if we have time, we'll also show you an application to real data here from Italy. So generated a finite population of 30,000 units from a multinomial distribution with 3 X's. Y is binary. X1 is just a quantitative variable taking 4 values. X2 and X3 are categorical variables with 4 categories. So we actually define them by 4 dummy variables. The number of unknown probabilities is thus 128 probabilities. We do independently samples, probability sample and the non-probability sample by use of Poisson sampling with selection probability. This is just the Reynolds formula. But notice that the selection of the probability sample and the non-probability sample depend also on Y, which I emphasized by the red color. And S either probability sample or the non-probability sample. Here are just the sizes. Then we generated a subset of responding units with response probabilities. Remember, for the responding units, there are no Y. For the probability sample, there are no Y values, only X values. So we again use the logic. And the response rate was something between 65 and 70%. Here are, we don't have to learn by heart. Both here are what are the different coefficients. Model 1 and model 2 are not very different. Remember there, model 3 is actually very different from model 1 and model 2. This is how we generated our data. And these are just the corresponding samples. So here I showed you the models, 3 different models that we did. Here I just show you three different models that we considered for generating the population, the non-probability sample. And what am I doing wrong here? And these are the corresponding models that we use for selecting the probability sample. So model one is the correct model generating the data. Models 2 and 3 are misspecified working models used for estimation. So we generated the data using model 1, but we assumed, in one case we assumed the correct model, but in the other two models, those are working models that are sort of misspecified. So how did we estimate the population probabilities? Basically 5 methods based only on the non-probability sample, based on integration of the probability sample and the non-probability sample in one method, reverse method, and the K&N method, where K, nearest neighbors, is defined the square root of the samples. In method 1, the empirical likelihood is maximized under these constraints. I wrote them before. Oh, that's a good idea. Can you hear me now? Yeah. Okay, thank you. In method 2, the constraint is replaced. So anyway, we use those constraints that I mentioned before. And for the application of the Team-Wang method, we use this logic model with all 3 variables. Here are some simulation results. To begin with, we have to estimate those coefficients of the response model. This is part of the likelihood. But here I just focus on those row coefficients. So you can see that the model 1 is the correct model. So we assume the correct model. And you can see that the larger the distance between the correct model and the model fitted, the larger the bias of the estimated response model coefficients. I'm not too happy with the estimation of row 1. 0.163 compared to 0.2, but anyway, this is what we got so far. Just to see how sort of close our estimated probabilities are to the true probabilities. It's a simulation study, so I know the true probabilities. So we use this Hellinger distance, which is defined there. And you can see that under the correct models, you get small differences, average difference as defined by this measure. Under the other models that assume that the selection to the non-probability sample only depends on X, and also under the models 2 and 3, you get, as you expect, larger differences. So try to use the correct model. So small values under the correct model, larger under the misspecified model, and under this missing at random non-response. Here are the mean and standard deviations of those coefficients. Remember that define the selection under model 1. So here I only consider the correct model. There are 10 coefficients altogether, because remember I have a coefficient of y. It's the last one. I have the first x, which is just a quantity variable. And then I have 2 variables, each defined by 4 dummy variables. So a total of 10 coefficients. And notice that the mean estimates are generally very close to the true values. So it seems to work. In the literature, when it comes to non-probability samples, there's always this concern about robustness of the model or the sensitivity of the models assumed to the model assumed for the sample selection probabilities. What I claim is that you can actually test the model that you assume, because what we have at the end of the day, we have data for the responding units, and we have a model that we assume for the responding units. So basically, you're in this classical situation where you have data, and you have a model that you fitted, and then you test the goodness of it, of the model. So this is exactly what we did. Here we apply the Hosmer-Lemeshow test statistic. And to construct the test, the sample is partitioned into G, approximately of equal size, based on the estimated probabilities of successes. So Y equals 1. And here is the test statistic. This one here, where OG is the number of observed successes in the group, NG is the size of the group, and mu bar G is the mean of the estimated probabilities of success. And though I have never seen a proof of this, but we verified it in many empirical studies, Hosmer and Lemeshow, they claim that it has approximately a chi-square with G minus 2 degrees of freedom under the null hypothesis that the model fits the data. So we apply the test under those procedures that we considered. And you can see when we tested the model either based only on the non-probability sample or by integration of the non-probability and the response data, we get p-values not very high, but much higher than 0.05, but are very low for the methods that assume MAR selection, and also very small under the model 3, which is really different from the correct model. As I wrote there, model 2 is actually not very far from model 1, so you still get sort of p-values on the boundary if you think it's of a 0.05 rejection rate. I considered before two different methods for estimating the population total. So we actually applied it. Again, this is a simulation study, so we know the true total. And you can look at the data there. Both estimators actually perform relatively well under the correct model. But the second estimator, this one there, has smaller bias and is much less variable. It also performs okay under models 2 and 3. Now, I just have to say here in the, what do I do? In this model here, I only use the data from the non-probability sample. Here I use the integration of the data from the non-probability and the probability sample. And cannot show you both tables in the same slide, but it shows that integrating the data results in lower bias of the estimators under the three models and lower standard deviations of this left-hand side estimator. So as long as you can integrate your non-probability data with a probability sample, you should go for it. Okay, I still have 9 minutes left. And thank you, Monica, for providing us with the data. So the non-probability sample, I just really very short description, is enterprises belonging to NACE, nomenclature of the economic activities, having at least 10 employees, selected from the statistical register of the Italian active enterprises called Asia. The sample contains information on number of employees, sales, NACE, geographical area, and Y is 1 or 0, whether it's involved in e-commerce or not. The reference time period is 2000, of the data that we had used is 2022, and the size is 51,000 enterprises. Our probability sample is called the situation and perspective of Italian enterprises during COVID-19. It's non-informative, and as far as we were told, it's not affected by non-response. I say I never saw a sample that doesn't have any non-response, but okay. Carried out by Istat with the aim of assessing the economic situation and specific actions taken by businesses to reduce the economic impacts of the pandemic. The survey was conducted in 3 waves. The last was between 16th of November to 17th of December. So this is what we consider in the present study. So the 2 samples don't refer to exactly the same period, but not too far. The sampling design used to select a sample is 2-stage stratified random sampling. Only enterprises with at least 10 employees and belonging to the NACE economic activities are considered, so it's the same as the non-probability sample, and the size was almost 20,000. Because of some operational limitation, we only consider the variable x1, the number of employees. And for further evaluation of the method, we divided X into 4 categories, 10 to 49 employees, etc. We computed the probability function of Z by employing the probability function of X, so the estimated probability of Z is just the sum of all the probabilities of X's belonging to the category Z. So here are the estimated proportion in classes Z obtained from the probability sample and the non-probability sample, and by harmonization of the 2 samples. Remember, you have the formula there, which can estimate the probability of X from the 2 samples. So what you can see, the first row, I mean, I should say what the Istat is. I just say the estimates are not very different from Istat. The last column contains estimated computed by Istat for 2022. The estimates were obtained from a sample of 30,000 enterprises, aiming to measure the degree of digitization of Italian enterprises. But even though you'll see there are differences, we should note that these are also just based on sample data. So to begin with, we estimated the selection probabilities to the S&P sample, the non-probability sample, and the standard errors. So this is the model we assumed. And here are the estimators, and you can see the coefficients are highly significant based on if you just use standard t-test. So clear indication of that there is a bias selection to this non-probability set. So for the methods that we considered in the simulation studies, we estimated the conditional probabilities, probability that enterprise I is engaged in e-commerce, given the group Z, is the expression. And again, you can see what you get. Notice that estimates you get by Kim and Wong and by River are much lower, again, because of this the only use of only the sort of only using the axes in computing the probabilities. And these Istat values are, again, same sample as in the previous table, in table 7. I'm only done. The HD is the Hellinger distance measure. If we take the Istat probabilities as being sort of benchmarks or for comparisons, so we computed the distance between the estimated probabilities and the Istat probabilities that I showed in the previous table. So they are 0.044, quite low for the method based on the non-probability sample alone, 0.040 for the methods based on the integration of the two samples, and then it goes up for the other methods. We again tested the goodness of fit of the model using the Rosmer-Lemeshow test. We send G equals 10 groups, and the P values are 0.09 and 0.08 respectively. So at least with those P values, we don't reject the correctness of the models that we have used. So here are just some concluding remarks. I think I'm perfect on time. Informative sampling and not missing at random non-response should always be checked and adjusted for both these probability samples and non-probability samples. So clearly, if you can convince yourself that the selection probabilities or the response probabilities don't depend on the Y values given X, you can obviously use all the other methods that I consider. Use of non-probability samples for official statistics, production of official statistics is not straightforward. On the other hand, the use of non-probability samples for official statistics are apparently inevitable in the long run. So I'm pretty sure it will be used more and more. Promises huge advantages which cannot be ignored. The procedures outlined in this presentation to deal with selection bias are promising, but only first steps. Much more theoretical and applied research is required. Here is just a list of references that I mentioned. Thank you.
Thank you very much. Now we can. We can open the discussion, the floor discussion, if there are any questions or suggestions. Please, Professor Sakocki.
Well, first, I really congratulate for the nice exposition. Of course, I couldn't grasp everything, but I have, however, three questions. One is, two are methodological, and one is on a special slide. As usually occurs in official statistics, there is not too much of Bayesian issues. So I was really positively surprised when you mentioned in a slide that there was a part that was Bayesian, and and later, it seems to me that the development of your exposition was rather related to the frequentist approach and to classical statistics. So, do you think that inserting that, let's say, relatively small part of Bayesian things important for your final results, or is this not so important? This is the first question. The
Can
second,
I answer this question?
no, but may I pose all the other?
No, I may forget the other one.
Okay, please, please. But yes, you are welcome, because I wrote the other questions.
I just don't remember that I mentioned the word Bayesian anywhere in my presentation. Generally speaking, I don't think that users worry too much about whether it's Bayesian or not Bayesian. They want to see the estimates that are looking for, and the standard errors. Here, by the way, I just a more general point. Usually the standard errors are considered under those quite complicated models, which users have no idea what's supposed to mean. The general public call it. But I think they are quite used about the design-based sampling errors. In other words, the sampling errors over all possible, say, non-probability samples or probability samples or whatever. So I always try to emphasize to actually compute those standard errors rather than under the model, because this is something that the users can understand.
Well, the second question is, you illustrated your method, and there was a kind of parallelism or comparison with other existing methods. Do you have the feeling that a kind of inbreeding may occur with the other methods? I was, for instance, more aware of the methods of 2007. And I am wondering if some ideas of the existing methods are already in your proposal, or there are, my question is whether there are some characteristics of the other methods that are not good for your solution. So this is my incapacity, of course, but I couldn't understand very well. So if you might explain some differences with the other methods.
I presented the other methods not to criticize them or anything, it's just to sort of show the importance of accounting for informative sampling or informative non-response. And as I said already, if you can verify that the selection probabilities or the response probability don't only depend on X and not on Y, no reason to use those more complicated models. And then you can just use the other procedures that I described, and there are several other procedures that are. So it just really, all I wanted is to emphasize the importance of accounting for non-informative non-response and selection if you actually sort of can check and verify that this is the case. Remember, in this actual practical application at the end, the coefficient of Y in this selection model was highly significant. Which means if you just fit the model as a function of the X and not of X and Y, then we haven't done it, but I'm sure that you get sort of incorrect results.
Oh, okay. Then I have my third question is really terrible. I apologize for this. But going to your slide 28.
Which one?
28. I had the feeling that the results are very, very similar. And so I was asking to myself, why?
Sorry, this one?
Slide 28.
38.
28.
So I am in 20.
I don't remember of what it was, but I saw that the figures was almost the same. And
Which figures were almost the same?
Yep.
Why doesn't
Yeah.
it, wait.
Because I noticed it only
Ah.
this, and I was wondering if the results of that slide were important or not. The interpretation of that page, I couldn't grasp.
Is it this one, this slide? I cannot hear you. Can you?
So, what is the comment about this? Are they similar or not, the last three columns?
What's the question?
If given, I felt that the results were very, very similar for the three
Yeah, they are very
models.
similar.
It is a good thing or a bad thing?
And they are actually quite similar to what we get under model
Yeah.
2 and 3.
Yeah. Yeah, this is
Just an
the
empirical
results. Yeah.
results in our
Yeah, okay.
simulation.
Okay.
Yeah.
Yeah. Okay, thank you.
Any other question? Yeah.
I wonder if you could say something about the effect of the size of the probability sample on the standard errors of your estimates of your variables of interest. In your simulation, if I understood correctly, you showed that if you don't use the probability sample, the standard error of your estimator is higher compared to an approach where you incorporate a small probability sample.
Which you would expect, because in the
I don't understand that. So
you use more data.
On the other hand, you calibrate. Yeah, that's probably not the right word.
In several slides, actually, I've sort of shown that the use of the non-probability, integration of the non-probability sample and the probability sample improves, perhaps not by much, the inference. Notice also that the non-probability sample is much larger than the probability sample. So it's not that you gain a lot of more information, but as I said, you expect to improve by data integration. So as long as you have a proper sample to integrate with your non-probability sample, then at least try it out.
On the other hand, you could claim that if you adjust the weights of the large sample based on the smaller sample, that could work the other way around.
If the non-probability sample is much larger than the probability sample, then, as I said, you would expect that integration won't help you much. But if in our case, I think it was something like 0.3, 0.27 in the simulations, the ratio between the sample sizes. So you can see that you can gain.
Mm-hmm. Okay, thank you.
First, thank you for your lesson. Very relevant topic, very well presented. I have a consideration and a question. Consideration is this, that when using non-probability data, non-probability sample, you have to inform users about the overall accuracy.
About what?
Accuracy of the data you are releasing. And so the methods should be even considered with the associated measure of accuracy, because for transparency, users should be informed about the error they can have using those data. The second, the question is, at the very beginning of your slides, I think third or fourth, you say that probability sampling is informative. And this sounds a little bit strange for me because
remember, in the simulation, also in the real application, the selection to the sample, there are no Y values in the probability sample, and the selection depends on X, and you want to estimate the probability of X. So this is informative. And I show you the equation. Hello. So it is informative because the probability your target variable in the probability sample is the X variable, and the sample selection probability depend on X. I can show you the slide again, but the probability of X in the sample is different from the probability in the population, which should not be the case if it was a simple random sample. Then, other than sampling errors, you would expect the same probability in the sample and in the population. Regarding your first question, this is a very good question, and unlike in classical survey sampling, where you can estimate the standard errors and you can even estimate the bias using resampling methods, etc., etc. In this non-probability sample, there are no selection probabilities. That's why you call it non-probability. So how do you actually report how accurate your estimates is a good question. I mean, I don't have a clear answer to that. Again, you can do some possibly in sampling, repeated sampling from the non-probability sample or this kind of stuff, but it's not obvious how you can actually convince people. One exception is where you have another reference source of data that you can compare with. So we had something like the Istat sample, which again is just a sample, but we could see that we didn't really differ much from those Istat values. There was only 2 or 3% difference between what we got and. But I don't know yet that there is any formal way to assess.
Thank you. Thank you for the presentation. A clarification on the role of X. So in the probability sample, it can be informative. So say as an example, it can be stratification. So the axis can just be the dummies for the strata. And then in the non-probability sample, is it that we're using the same axis, or is it possible that in the set of the axis you put other axes that may influence the non-probability sample? Or is it just that it's the same set of axes in both models? And so the only difference is that in the non-probability sample you have Y, or?
Yeah, in the non-probability sample you have Y, which you don't have in the probability sample. In the simulation study, we use the same axis. In other words, we generated a population with axis, and then we had a probability sample from that population, and the non-probability sample, which is sort of supposed to be a sample from the same population, but with selection bias. So in this respect, the axes are not exactly the same, but they're at least supposed to be sampled from the same population. I don't think that we anywhere require that we have, for the use of the empirical likelihood approach, you have to assume that the support of the population axis is in the sample. So you do observe the same axis, obviously not with the same probabilities, but basically the two samples cover the population excess.
Thank you.
May I ask a question myself? Thank you very much for the presentation. In both the selection and the response model, you have been choosing a parametric model, say logistic, a probability model. Should we try to find something more fine in the prediction of these probabilities, or should we go for a simple linear model? In the sense we should insert interaction.
About the selection model?
Yeah.
Again, we use logistic, and by the way, there is a nice justification for the use of logistic model. There was a very famous mathematician, Weierstrass, I think in the 19th century. And he basically had a theorem which is similar to the Taylor theorem for continuous variables. So basically, he shows that if you include in the logistic model, so the true model is something, and then if you included the logistic model, or the main and interactions, etc., then you can make the difference between the two models as small as you wish. I mean, by adding more and more, and as the sample size increases. So it's something like, I'm not formulating it here exactly, but it's something like the Taylor approximation. So, but you can use other models, and you can try several models and see, compare them like we do in classical statistics.
Just to understand, the role of a very good estimate for this probability is necessary or not? Should we go for a very precise estimate?
So again, as I said in the literature, also Jay in his articles, I mean, people very often raise this issue of how sensitive the inference is to the choice of the correct model. As I said, I mean, I'm not saying this is not correct or anything. All I'm saying that you can actually test your models. And again, I just showed one possible test. We tried also just a classical test, chi-square test, etc. So you have some idea of how your model performs. I don't know. I mean, ideally, you do indeed sensitivity analysis, try different response models, and then compare the results. And if you see that final estimates are not very sensitive to which procedure you use, then you're okay.
Just a theoretical curiosity about your test. Is it consistent in the sense that as long as the sample sizes increase, does the probability of rejecting a false null tend to 1?
Sorry, I didn't listen. Ask it again, please.
I'm referring to the testing procedure based on a chi-square test, essentially. Okay.
The testing procedure?
Yes,
okay.
Testing procedure. Is your test consistent in the sense that as long as sample sizes, possibly of both samples, infinity, does the probability of rejecting a false model tend to 1?
I must say, I'm not familiar, and ask people of any theoretical properties of this test statistic. I do know that in several articles that I have authored, we actually compared under the correct distribution, the empirical distribution, because we say they had 500 simulations, so we could see what is the empirical distribution of this test statistic. And we compared it to the chi-square distribution with G minus 2, and the fit was almost perfect. So it seems to be okay, but again, I'm not familiar with and it's a very popular test. I know in sociologists, etc. They use it a lot.
Any other question? Okay, so let me thank again Professor Pfefferman.
Thank you. Thank you.
If I'm not wrong, should be the coffee break now.
There is a coffee break now. It's just outside on the left, and we have to be here at 11:20.
So hi, if everyone can sit down, we are going to start in 1 minute. All right, good morning, everyone. My name is David Haziza. I'm from the University of Ottawa. Welcome to this session on methods for multi-source statistics. We have 3 papers today, all investigating different aspects of integration of surveys. One paper is on the different sampling designs. Another one is on measure of accuracy for multinomial variables based on linearization method. And the last one will be on the use of MNO data, right? And how to use MNO data to predict the flows. And so we'll start with the first paper. And the speaker will be Silvia Lorega from Istat. And and then this will be followed by a discussion. And the title of the talk will be the Integrated Census and Social Survey System Project.
Thank you very much. Okay. The work that I'm going to present regards the work that we are conducting here in Istat about the optimization of surveys. And in particular, it regards the Integrated Census and Social Surveys System project. In this presentation, I will present the context for this project, which is the main aim, which was the initial design of this system, and the advantages of one particular scheme for the sampling design of the surveys. And we will see which is the current implementation of this system in Istat. After that, I will present the results of 2 experimental studies that have been conducted this year in Istat. The first one regards the 2 phases sampling scheme, and the second one regards spatially balanced sample selection. I will conclude with some final remarks. The context of this project is the design of multi-source processes. In particular, as regards social surveys, we have sample surveys and also administrative sources that are organized in registers. And the idea is to study how to design the statistical processes in an integrated way in order to exploit the advantages of the different kind of sources. The integrated census and social survey systems that in Istat we named as SICIS is composed by three main elements. The first one are the social surveys that are focused on specific subjects. They produce annual or infra-annual estimates, and they are able usually to obtain estimates at a low geographical detail. The key element in this system is constituted by the permanent population census that plays a central role in this context because it aims to produce a consistent framework for demographic and socio-economic statistics. It produces annual estimates with high geographical detail. The third element is constituted by the integrated register system. The registers are built integrating administrative sources, and they are able to produce direct or indirect outputs. It means that these outputs are used as input in different estimation processes. Through the registers, it is possible to obtain a maximum detail because they are available at the level of elementary statistical unit. Which is the core idea? Is the design of the sampling strategies for social surveys in an integrated way. This means that the features of sampling strategies, such as sampling schemes, direct and indirect estimators, and smaller estimators, can be designed from the beginning in a multi-source statistical production process. The aim is to improve the estimates in terms of accuracy, granularity, and coherence. And the key element is to consider jointly the implication and the strategic choices for data collection and thematic objectives. We can ask why we decided to start studying, to start this project to improve the efficiency of social surveys. The current sampling design that are used in Istat are not already chosen to maximize the efficiency, and why we should also reconsider the survey techniques for the social surveys. The question regards mainly the overcoming of the stovepipe approach in the design of these processes towards a systemic perspective in which the integrated solutions are found for different surveys and taking into account the different phases of the surveys. The aim is to evaluate potential improvements for sampling design, estimation, methodology, and survey techniques, exploiting auxiliary information, And also, an important goal of this project is to analyze and to find solution for some identified issues that we currently have in data collection, mainly the undercoverage of telephone list, that is a problem to conduct CATI interviews, and the increase in total non-responses. The initial design of the CSIS consisted in a modular approach based on the two phases sampling scheme. In the first phase, we have a general module to collect the target variables for population census. And in particular, the population census, the list survey for the population census, is based on a large yearly sample, and we referred to as the master sample. At the second phase, specific modules are designed in order to observe the target variables for the other social surveys. This means that the other social surveys are based on sub-samples of municipalities and households selected from the master sample. Which are the advantages of such a scheme? First of all, is the leverage of the information collected in the first phase as auxiliary variables in the second phase, in the design, in the calibration, to correct for non-response, and also for smaller estimation. Also, there is the leverage of repeated observation on the same variable over the same units in both the phases. That, for instance, can be used to estimate measurement error models. The leverage of phone number or email that can be collected in the first phase that are useful to conduct CATI or CAWI interviews in the second phase surveys. And the leverage of structural variables collected in the first phase in order to lightening the questionnaire in the second phase, for instance, asking for this information just for confirmation or to change some mistakes in the first phase data collection. Which is the main disadvantage of this sampling scheme? Is the response burden. Because households are contacted at least twice in order to give the information for the first and the second phase surveys. Here I describe the current implementation of CSIS that is not complete because, currently the initial design has been applied for just 3 surveys and in a partial way. For the labor force survey, we have an overlapping with the master sample of the population census just at the first selection stage, so for just the municipalities, except for the smallest one. For the aspects of daily life survey, the one that is named AVQ in Italian, from 2018 to 22, we selected the sample for this survey as a subsample of the master sample, both at the first stage and the second one. So the municipalities and the households are subsamples of the master sample. Since 2023, the overlapping is just at the first stage. For USILC, we selected the subsample completely as a subsample of the master sample. It is worth noting that till now, we didn't exploit the overlap between the first and the second phase surveys during the estimation phase. So, taking into account this state of the art, we thought that there is the need to evaluate this current implementation and to rethink the entire system. Here I'm going to present 2 experimental studies that we conducted during this year in Istat. The first one regards the 2 phases sampling scheme that I just mentioned. And the aim is to compare the efficiency of different scenarios for integrating the first and the second phase samples. And we focused the experimental studies on 3 surveys. The first one, of course, is the population census master sample for the first phase. And for the second phase, we explore the implementation for the labor force survey and the aspect of daily life surveys. And okay, the second experimental studies is focused on spatially balanced sample selection. And the aim is to evaluate the efficiency gain coming from a spatially balanced sampling at the first stage, the stage of the municipality. And we adopted a 2 stages sampling design similar to the LFS, but similar also to most of the social surveys in Istat. And what is a spatially balanced sample? Is a sample that is balanced with respect to the available auxiliary variables, and it is also maximally spatially distributed. Let's see the first experiment on 2 phases sampling design. We simulated 3 scenarios. In the first one, we simulated no integration between the first and the second phase. In the second scenario, S2A, we integrated the designs, but just at the first stage, just for the municipalities. In the third scenario, S2B, we integrated both the stages, also for the households. We compared the efficiency of the different scenarios, taking into account 3 estimators: the Orvis-Thompson, a first calibration estimator in which we use only demographic auxiliary information, a second calibration estimator in which we added also auxiliary information coming from the master sample, from the first phase. The target variable is the employment status, and we assumed that we had full response and no measurement errors in these simulation plans. This experimental study has been conducted by Alessio Guandalini and Manco Dionisio Terribili. Here in these slides, I presented graphically the different scenarios. It is better to go on. And as regards to the simulation plan, we focused the simulations on 3 regions. We did 500 replications for each design and for each estimator, and we used R software. Here, the first main results. We have the estimated coefficient of variation for an estimation of the total number of employed individuals in the total of the 3 regions. And here we can see, comparing looking at the different integration scenarios and looking at the different surveys, comparing the performance of the 2 calibration estimators, we can see that we have a modest overall impact of the integration with the master sample for both the LFS and the aspects of quality life survey. And looking more in detail and looking at the impact of the design and of the estimator, looking separately to the design effect, the estimator effect of the calibration, and the additional estimator effect due to the use in the calibration of the auxiliary variables coming from the master sample, that is the last column, we can see that we have a design effect that may be considered rather high for the different surveys. In particular, it is higher than 3 for the LFS, higher than 2 for the aspects of quality life. In In case we adopted the same stratification that we use for the aspect of quality life survey over the sample municipalities selected for the master sample, we are able to reduce the design effect for aspect of quality life to 1.3. Using the calibration estimator simply with demographic variables as auxiliary variables, we are able to compensate the design effect, but also we are able to improve furtherly the efficiency, introducing in the calibration also the information coming from the master sample. In particular, in this case, we used the educational level collected by the master sample in the calibration for the estimation of the employed persons. Further results that we obtained in this simulation is the increasing, is that if we increase the overlap between the master sample and the surveys in terms of municipalities, we improve furtherly the efficiency. Further developments that we already planned is taking into account of non-response mechanism, assessing the impact on the different surveys and using as auxiliary variables information from the registers. The second experiment is on spatially balanced sampling design, and the aim is to take into account the spatial dependence of statistical units in design, maximizing the spatial distribution in order to capture the spatial heterogeneity of the population of interest. We used indicators for the different municipalities coming from Archimede database, in particular the socioeconomic conditions of households. That is a database composed by integrating different administrative sources. In particular, from this database, we are able to use income variables and labor market variables. And also we used some estimates at the municipality level coming from population census, in particular for demographic variables and the distribution by educational level and by employment status. The parameters that are estimated are the mean of the variable of interest, and the estimator is Orbis-Thompson. We compared different sampling design. The first one is the benchmark sampling design. That is the one that is currently used by most of the social surveys. That is a two-stage sampling design that I already described. And the three other designs are spatially balanced designs that are implemented using the local pivotal method. And what changes in the three between the three designs is the stratification. In the first one, we adopted the same stratification at the sub-provincial level. In the second one, we stratificate just by provinces, and in the third, by regions. The simulation plan was conducted over the entire national territory. We did 10,000 replications for each design. We used our software. Okay. I would like to mention that this experimental study has been conducted by Roberto Benedetti, Federica Persimoni, and Monica Russo. And here are the main results. Just 1 minute, if it is possible. We obtained that spatially balanced sampling is more efficient just at the first stage compared to the stratified design, and the efficiency gain is greater for variables with a higher spatial correlation, and is higher if we adopt a less fine stratification. So stratificate by region is better than stratificate by province or sub-provincial level. In particular, for income variables for which we have a very high spatial correlation, we have very high efficiency gains. More or less 30% of the variance with the stratification at the provincial level, and 50% at the regional level stratification. For the labor market participation, the spatial autocorrelation is a bit lower, and also the gain are a bit lower. For demographic and family variables, for which we have the lowest spatial autocorrelation, even for these variables, the efficiency gains are more than 25% with the regional stratification. An additional advantage of this kind of design is the coverage of unplanned territorial domains. I'm concluding with final remarks. The next developments of this project will focus on the main issues emerged in data collection, mainly the increase of no-response rates and the need to rethink the data collection techniques. It is important to underline the work approach that we think is needed in this context. We think that methodological and operational strategies have to be studied jointly, and we think that a systemic perspective for the different surveys must be adopted. Currently, an important added value of this project comes from the collaboration between the methodological and data collection teams in Istat. We think that a further step towards adopting a fully systemic approach must also involve collaboration with the teams responsible for data production. Thank you to everyone who collaborated to this project in Istat, and thank you for the attention.
Thank you very much. So we'll go directly to the second speaker. Yes. So our second speaker will be Stefano Falozzi from Istat, and the title of his talk will be Linearization Approach for Measuring the Accuracy of Multinomial Outcomes from a Statistical Register.
Good morning. Thank you for inviting me to have this presentation. This work is a work. I present a work that was in collaboration within a collaboration with University of Roma. And these are the other authors, Diego Chianella, Romina Filippini, and Simona Toti, and for the university, Giorgia Leva, Nina De Liu, and Piero Demetrio Falorzi. The contents start from consideration that one of the pillars of the modernization is the integrated system of statistical registers. Within this statistical framework that is servicing all the production of statistical, all the statistical production at Istat, many of the variables are obtained within this framework through multi-source statistical processes. We have already seen this framework in the previous presentation within the thesis. In the work, we present a generalization of the work presented by Alle et al. In 2021, in which is proposed a generalized mean-square error accuracy for planned and unplanned domain. Important is also unplanned domain that may be computed directly by user reading the producing estimates, their own estimates from the available registers. This is most important for official statistics. And we present an application on the attained level of education by means of mass imputation based on multinomial distribution. This is part of base registers of individuals. And with this statistics, with this indicator, we are going to produce other the accuracy also of other census variables like non-employment status. At the end, we make a comparative analysis of empirical properties of GMEC versus Bootstrap by means of Monte Carlo simulation using synthetic data generation from attained level from the base data on attained level of education. This slide is a representation of a multi-source statistical process in which we have administrative data and survey data that contribute to the production of base register and satellite register. The release of each statistical register is based on multi-source processes that mainly integrate administrative data and also surveys. This innovation has led to create new processes that can vary a lot in a complexity. Then there is a need of a new proper quality system to assess and monitor the new processes and their results, has been expressed from several points of view. In particular, in this paper, we focus on the production of single indicator that give us also to the user an easy, immediate measure of the quality of that indicator. The estimates obtained from the statistical register should be associated by a measure of their uncertainty. It is difficult for traditional sample survey to produce accuracy measure that take into account different error sources. This is even more challenging for estimates from statistical register. These estimates include different component of variability. In particular, as we have seen, we have the contribution of sample survey data with their variability together with administrative data, and they are integrated by means of models. So it is important to produce estimates also for unplanned domain and to calculate also a measure of uncertainty for on-the-fly estimates that should be produced by the users. In this slide, we have an overview of different variables that have been produced during the first cycle of the census during period 2018-2021 by means of integration of administrative data and survey data. So we have level of education, employment status by means of level of education by means of generalized linear models, and so on, by means of different application of different models. The setup, the basic setup is that we have a register the true values of the variable of interest. We may have a situation of over coverage or under coverage that and we have predicted values for predicted values obtained by means of a model linking the auxiliary variables and the variable of interest that in general is studied linking the survey data with the variable of X available on the sample. So we have a working model. In this presentation, in this work, in particular, we focus on the attained level of education, which is part of base register of individuals that has different pieces of information. We have administrative information coming from the Ministry of Education. We have census starting from 2011. Onwards with 60 modalities. Census information on educational status collected in 2011 census with 12 modalities. And then we have the sample surveys that is carried out every year since 28 with 7 modalities and other auxiliary information related on attained level coming from transfer of residence. The aim is to estimate, to obtain an estimates with reference to K equal 8 categories of attained level. This is in this slide. The figure shows that we have for some characteristic, we have a complete information, red, individual characteristics known for all population of interest, gender, age, class, citizenship, and so on. Yellow, is partially available, and green is missing data. So we have different framework, different for the production. So we have to apply the estimation with different subset of information. The reference models is a mass imputation procedure to obtain to estimate the attained level of education by means of multi-linear model. So this is our reference model. So the integrated system or register does the result of statistical processes subject to different sources of statistical uncertainty, sampling uncertainty, model uncertainty. In the paper of alle 2021, they which is the paper, the reference paper that we have extended. The initial idea is to produce a general measure of variability, developing to develop the idea of global, to produce a global measure like in Walter 1986. And also developing the concept of anticipated variance, like in for papers like Isaki in 1982 and Tillet and the other, I don't remember, in 1980. I will give Then the idea is to produce a global measure. The idea is also the idea of total survey error, taking into account different sources of variability. Okay. Then the setup. We have a parameter of interest that is a total referred to of variable y referred to a domain D. D is a domain indicator, and the vector y is modeled as a multinomial model by means of multinomial models depending on a vector of unknown probability. So pi is the unknown parameter vector. Then theta hat d is the corresponding estimator referred to domain D, in which we obtain that the predicted values are obtained by means of the estimates of the coefficient, the parameter of coefficient of regression, beta hat. This is under multinomial model. The pi hat is expressed by the well-known formula under multinomial model, depending on a J set of covariates. The goal is to estimate the accuracy of theta d hat using a measure that can be produced easily from for each estimate. So it can also use it for on-the-fly register. The other, the competing techniques may be bootstrap techniques, that is more problematic in terms of times of computation. The idea of global mean square error is to take into consideration all the random components. And we focus on two sources of uncertainty: modal variability and sample variability. Lambda, this is the sample in the expression. This is the expression under different and under P random components, and we focus on the expected values of the expected values of the expected value under the sign of the variance under the model. Lambda is the vector of sample indicators. So it can be shown that GM is a conservative expression of the GMC is the expected value under the design of the variance under the model. And this is the formula for which we work on. So we focus on the diagonal components, on the variant components of the general mixed cross product error related to the variance, not considering covariance components. We have to, in the paper, in the work done, and last work, we show that with reference to the original paper of alle et al., we show that it is enough to linear approximation of the estimator is with respect to the original formulation with 4 steps of approximation. In particular, we have the expression of estimator of the variance that is linearized around beta hat for beta equal is linearized at beta hat equal beta by means of Taylor approximation, and then the results in the second linearization, there is a linearization of the term beta hat minus beta using the Chambers-Clark result. So we have two steps of linearization. In the original paper, the other is showed that the other 2 linearization with respect to lambda belonging to the sample or not, it has a minimal impact on the quality of the indicator. So this is the final expression that is composed by Fk, that is a component depending on only on the covariates, not depending on the variability of the not depending on the variability, and the central part depending on the variance on the variance covariance matrix of the variable. In order to get a more computational efficient estimation, we have already proposed a Kronecker formula based on more compact expression and more compact matrix expression. Simulation comparison. We have tried different population sites and different sample sites with K equal 8 categories and J equal 14 covariates. And we have used as gold standard reference Monte Carlo. We have tried Monte Carlo simulation with capital G independent replicas and M of the sampling design and capital M replicas of response variable for each sample replicate. This is the setup, the auxiliary variables. These are the true coefficients of regression for each for each category. And this is the first we have produced this is the simulation in which we have calculated the linearization, the GMSC, matching with Bootstrap, that is another competing technique, and with the Monte Carlo. As you can see, the GMSC is very near to Monte Carlo for each population, for each scenario, and in particular Bootstrap is the competing techniques as a slight overestimation in general. Also, it is important to note that for extreme categories like illiterate at PhD level, the estimates follow are larger, are larger for smaller quantities. This is also this also shown in the in this graph, in which you can see that Bootstrap is blue, GMSC is yellow, and Monte Carlo, the reference, is the black. In this slide, we show that general mean-square error is a measure more stable and near to Monte Carlo estimator, Monte Carlo reference. Conclusion. In this work motivated by Istat program, we took our first step to evaluate the feasibility, validity of global measure of accuracy. Key advantages: computationally and memory efficient, allows on-the-fly estimation. Ongoing and future work: extend and evaluate the GMSC to other structure of data models. Consider other methodological developments, such as the case of latent class models that is applied, for example, for the estimation at Istat of employment by means of registers and administrative data and sample data. Bayesian framework to incorporate additional uncertainty arising from the a priori distribution of model parameter used for prediction, provided implementation support. These are some reference, and this work is the result of the collaboration of many colleagues. Thank you to all of them.
Thank you very much. We'll go directly to the third speaker, who is Tiziana Toto from Istat. And the title of the talk will be Combining Survey Data and Mobile Network Operator Data for Commuting Statistics.
Thank you so much, Professor Aziza. Good morning to everyone. This is a joint work with several colleagues of mine that you can find in this room, and Professor Li-Shun Zhang in his dress of Chief Methodologist at Stat Norway, rather than as a member of the Methodology Committee for Istat. And these are actually it's a work that started in a research project co-founded by the European Commission, the ESSnet MNO Minds, where MNO stands for Mobile Network Operator Data and Minds for methodology for integrating new data sources. This is the credit we have to pay to Europe for these projects. It's a project in a larger set of initiatives that the Statistical Division of the European Commission is taking in order to reuse these mobile phone data, as they also are called, for official statistics production. So there are a lot of initiatives connected to this specific task. And as you maybe already know, after the presentation from this morning of Professor Pfefferman, these mobile network operator data are obviously a non-probability sample. And in the research project Minds, we are tasked with identifying which kind of a methodology and develop new methodology if there is a need for using this data in the specific context of official statistics. So a little bit different from some other experience outside the official statistics. We start our work on methodologies with the literature review, with the literature appraisal, and with clarify what is our approach for the reuse of this data. And in our approach, since it's born in the official statistical context, we put the total error at the center of the frame for the identification of the methods and the methodology. Total errors are connected with the statistical unit, with the target statistics, with the data configuration. I suppose everyone is aware of what mobile network operators are actually the event collected by the antenna of the mobile network that records actually all the events between the device and the antenna itself for operating the service, the internet, the phone, whatever. So the data configuration could be very different in using and reusing those sort of data. We can have nano data, micro data, aggregated data, and all those aspects have an impact on the methods that we may or may not apply. And another important component of this reference frame is which kind of use we want to do for the MNO data. There will be our primary source, there will be an auxiliary information, there will be a proxy information that is somehow different from auxiliary, you know better than me. So all those aspects are, in our view, reorganized according to the main source of uncertainty, and this identify our three main pillars, branches for classifying the methods: the randomization, the quasi-randomization, and the superpopulation modeling. Those would be also the way in which I will classify the methods that I will show you in a while during this presentation for the specific application we propose. Of course, the first one, randomization, is not into the analysis for today because we cannot run a sample survey based on MNO data for this application, but quasi-randomization and superpopulation will be the one I will explore more in the next slides. Which is the target of the application that we propose in this specific case of reuse of MNO data? It's something really important for the National Statistical Office, is the commuter origin destination matrix by municipality. In Italy, we have like about 8,000 of municipalities, so the complete matrix is quite a big one. We apply the definition of a commuter according to official statistics. It's someone who live and go back to home in the same day at least 3 days per week. And the reason why can be distinguished between work and study. In our application, we do not distinguish between work and study. They are collapsed together. And clearly, this is a very complex task for an official statistical office for producing this. We approach it in steps, where the first step is identify the commuters that go out of a municipality without distinguishing the destination. So it's an outgoing flow, regardless the different destination this outgoing flow can take. How we usually deal with this complex task in official statistics? With census data. Census data is a complete enumeration. Even the not frequent or very few flows can be identified if you take a census. But as maybe you already know, in Italy, in Istat, especially since 2018, revised the census strategy. We do not have anymore a traditional decennial census. We move to a census based on survey. It's a 4 years round plan. We have some representative municipality in the sample every year, and we have also some not self-representative municipality organized in strata. Stratum are composed by 4 municipalities. One municipality participate to the sample every year. So since 2018, producing the commuter matrix is not a trivial task, because we have municipalities that are not in the sample for census. So in around 2021, when Eurostat asked Istat to produce the origin destination matrix, we have to find a way based on a survey rather than on the complete enumeration for produce this origin destination matrix, knowing that some municipalities have not been observed. So the outbound flow and somehow also the inbound flow for this for these municipalities have not been included in the observation, in the direct observation. So here it comes the MNO data. They can provide a very useful insight on this flow, because we know nowadays everyone has a device with him, her, when moving, when working, when studying, when at home. In the specific application that I will show you later on, we use something that we can use. It's not the ideal situation. And it is our is a application scenario, is not the application that we would do if we can ask directly to the MNO to provide us the data that we would like to have. But it was we can do in order to somehow prove, demonstrate, look at how they work, the methods that we have developed in a most close to the real case situation, not the ideal one or the one that we would plan if we can. We have these call detail records that are the one originated by phone calls and text messages. So it's a specific kind of activities that the antenna record from our device. It's not all the kind of activities that the antenna recently recalled that are the signaling data. We observe, we have a sample of this data in 6 weeks in 2017 in one region, Tuscany. So actually, this is the focus of the analysis that we are doing. The time gap between the MNO data and the target statistic reference time may play a role. The data from this non-probability sample is expected to be updated as close as possible to the reference time in a quasi real-time manner. This is not the case of our application, but this is what we can show you for the time being. Then we have other information, like as we had at the National Statistics Office. So we have a lot of information. We have the previous census round. It's out of date. It's 2011. It's complete. And there is also something to remark, that is commuting patterns doesn't change too much in time. So they are quite stable. It's not really a phenomenon with a high level of changes. Then we have some administrative data on the residence place and also the place of work or study. They have been prepared ad hoc for the purpose of the census production 2021. So it's a result of a huge work made within the national office. And then we have some municipality features. We can consider them freely available, open source data. They are related to the population size, the availability of means of transportation, so the distance between municipality in terms of space, but also in terms of time and so on. So those are quite important. And this is for completing the background, our notation. So the origin destination matrix can be actually represented as a matrix where Y is the number of commuters from municipality in position row and municipality of arrive destination in the column. We can stack this matrix and produce a vector of the flows ordered by origin. We, in our application, do not consider the main diagonal, that are the commuters within the same municipality. They are actually not negligible, is the most part of the commuting, but we decide to remove the main diagonal from the analysis because we consider that maybe the MNO data are not the best way to fit this purpose because observing this maybe not apply to Rome, where the municipality is very big and moving up and down in the Rome municipality can be registered by the antennas, but in small municipality, like the majority of the Italian municipalities, the level, the granularity of the data cannot be enough for MNO data cannot be enough for registering into intra-municipality flows. So the size of the vector we want to analyze is capital N, that is n at the power 2 minus n. In the first step, when we only analyze the outbound flow, actually, we only analyze the vector of the sum given by rho. So this one. How to deal with this issue in this task in a modeling perspective? A quite natural choice could be these interaction models proposed by Lassange Pace in 28, where actually the target measure is represented as modeled via some features of the origins, some features of the destination, some features of the friction, that could be the distance between the origin or the destination, the time, and so on. There is a quite interesting and hopefully useful extension of this basic model that also consider spatial autoregressive components that can, where can play a role the autoregressive component on the destination, on the origin again, and also in the matrix that I call D here, we can add some auxiliary information, not only the distance, and for those auxiliary information, actually, we mean the flows, the MNO flows, the administrative data flows, and so on, the previous census flow, and so on. We can add a area level component to this to the previous model, considering a Fay-Elliott model, where actually the autoregressive component can only be applied to the vector of the U, the random fixed effect. And this would be the modeling strategy in this case. In this case, there is a simplification, only the destination autoregressive component is included, but this is only an example. And the same approach, the spatial modeling, the Fay-Elliott model, can be considered also if we remain on the first step of the analysis, considering only the outbound flow. So instead of considering the matrix, we only consider the vector of the commuters originated from a municipality. Similarly, for the auxiliary information, instead of considering the flows, origin destination for the MNO, the admin data, the previous census data, we consider the vector of the outbound flows. And this is what we can do with modeling, but still we have the big issue of the not observed municipality in the case, in the real case of the survey census for 2021. What we can do for the not observed municipalities, we can somehow improve the synthetic estimation that would result from the Fayerot model for the non-observed domains with a transfer learning approach, when actually we distinguish between observed D1 municipality or area or domains, and not observed municipality or area or domain D0. And we are able to estimate the parameters for the coefficient and for the variance of the random effect on the sample. We also have an EBLAP estimator for the target variable YK in the sample. But we want to improve the estimate of the random effect out of the sample, minimizing somehow this function, where a crucial role is played by this distance between the result of the EBLAP on the variables that we put in the model, and a proxy variable of the target measure Y, which is available for all the domains. And minimizing this, so we can somehow improve the U vector outside of the sample. How to do this? How to choose this tuning constant alpha? On what we have, so on the sample, and on the basis of the EBLAP results for U. So our approach is to fix some values for alpha, measure the U tilde alpha that would be obtained minimizing the function on the sample that we have, D1. And then we will choose among the set of proposed alpha, the ones that correspond to the U tilde alpha closest to the EBLAP 1 in the D1 set of municipality, closest according to some metric. I will show you how it works later on. Leaving the modeling approach and moving to the quasi-randomization, we can estimate somehow the pseudo-probability of being included in the MNO sample, if the MNO would be a sample for which we ignore the selection mechanism, via this ratio that is actually the proportion between MNO and target statistics at the level at which the statistics is considered reliable. In principle, we will compute this adjustment factor, this pseudo probability, in groups that account for the heterogeneity of the MNO data and the heterogeneity of this ratio itself. But actually, we don't have those information in the MNO data that we have. We only have geospatial information, so we can only apply this adjustment considering the space, not other relevant information like age, that is one of the results of the research project. Age play a role, of course, in the probability of having a phone and using it. We can also apply another kind of quasi-randomization approach that instead of relying on the result of the survey, like in this case with the y-hat, we rely on some external information. For instance, adjusting for, again, the target population, the proportion of subscribers of the MNO, and some duplication adjustment, because we know that there are people without a phone, but there are also people with more than one phone. Those adjustments require external knowledge, so again, they would be more effective if we can identify some homogeneity groups. This is not the case in our specific MNO data, but this is only a case how to achieve reliable adjustment at a very detailed group level. Some results. This is the relationship between the direct estimates and the covariates that we consider. The blue are the MNO. They are at the slope that is lower than the other because we only observe one MNO, while the relation with the previous census and the admin data are much closer to the main diagonal. I have to go very fast. Those are the direct estimates that are not so bad, both in 2021 and 2018. In 2018, we can improve a little bit because the sample is smaller. By the way, the problem is not only the direct estimates coefficient of variation, but is the out-of-sample municipality. We have to do something for the out-of-sample. Those are to show you very honestly that the MNO data alone seems not enough for providing results, but they improve when the other data sources when we add the MNO to them. So there is a worthiness in using them. Those are the mean square error of the direct and Fayette application in 2021 survey. So again, we improve somehow, not too much, but at least somehow the direct estimates. And this is a picture where I assume you are not able to appreciate the shades of blue and red colors, but again, those are the estimates we can provide, and now we have in the not easy situation to say which one we prefer. This is something more on the to show you how the transfer learning approach works, actually as a smoothing compared to the EBLAP or synthetic estimates. For the conclusion, I can skip it because I fully agree with the conclusion provided by Professor Pfefferman early this morning. Those are some next steps we would like to explore in the next future during the research project months. Thank you everyone for your attention.
Okay, thank you. First, I would like to thank you for the opportunity to discuss the paper. So I'll try to keep it very brief, maybe 3 minutes per paper, because we are a bit behind. So those are the 3 papers. Yesterday, the order has changed, so 2 became 3 and 3 became 2, but I'll still discuss this in this order. All right. So in the first paper, the idea was to explore a new CSHIS designs because the one that has been used based on modular approach has some issues, and in particular respondent burden, right? So the study considered two types of sampling design. So the first is the two-phase sampling design, and then the spatially balanced sampling. And then the two empirical studies were conducted. For the first empirical study, we had the three samples: the master sample, the LFS, and the AVQ. And the authors considered three scenarios: the no integration, some integration at the first phase, a bit of integration, and then fully integrated, called S2B, where integration in both stages. And they compared three estimators, Cal1 and Cal2, Cal2 being also, in addition, calibrated on the master sample, some variable ALE on the master sample. And what we see in the results, and this is the result from the paper, is that this has been mentioned, for a particular estimator, let's say Cal1, in fact, what this shows that integrating or no integrating, so having no integration or fully integrated, it doesn't have a big impact. In fact, there's very little impact on the coefficient of variation. And this is true for LFS, but also true, these values are pretty similar to each other. So that's the first remark. And the second remark is that for a particular design, the choice of an estimator Cal1 and Cal2 is also very mild. The CVs from, if we look at column 2 and column 3, are pretty similar in all cases. And so this is where I have a question and probably a misunderstanding and so maybe the author can answer, is that in table 2.2, and this was shown during the presentation, so we have again, so this is for a subgroup and we have again Cal1 and Cal2. And here we have the design effect. So this is design effect with respect to the Horvitz-Thompson estimator. And what's called estimator effect is the gain we have by using the Cal1 estimator. And MSc est effect is the additional gain we, from the Cal1 to the additional gain we have by using this calibration on the master sample. And my question, one of the questions I had is that in the first table, we see that there are essentially no difference. Whereas here we see that Cal1 and Cal2 are pretty different in some cases. So I was wondering why here we have a significant difference between Cal1 and Cal2 that we didn't see before. Is it because it's a subgroup? And one of the questions I had is that at the regional level, we didn't see much difference. But what happened if we, do we still have the same result if we are at a smaller domain level? Does Cal1 and Cal2 and integration, no integration make no difference or no difference? And so here we seem to have a difference between Cal1 and Cal2. And the other thing that I've not understood here is that here Cal1 and Cal2 have essentially the same efficiency. Still, the two columns here are different. So we are improving. 0.28 means we're improving a lot with respect to Horvitz-Thompson here. And here we're saying that we're improving by using Cal2. But those two columns show that they are the same. So I don't see the improvement here. So maybe there is something I'm not understanding. The good news is that if we use if we re-stratify, this was what was shown in the presentation. If we re-stratify, then we are able to get a design effect close to the non-integrated one. So that's good. Now, in the spatially balanced sampling, the second study, in the previous design, the assumption is that municipalities with approximately same number of people have the same behavior with respect to the variable of interest. In the spatially balanced design, now we are saying that neighboring municipalities have the same behavior. So we changed the approach. And the author used the local pivotal method, which tends to favor to select the selection of municipalities that are spatially distant from each other. And 6 types of continuous indicator, income variable, demographic variables, and so on, were used. and they use the Moran's index to measure the spatial question. And the nice feature is that here we had a wide range of Moran's index. Of course, the income variables had a high Moran index, and the demographic variable had a low Moran index. And then three different spatially balanced sampling design were tested, and they were based essentially on different stratification. And to my surprise, I mean, I was not expecting this, but the gains were significant by using the spatially balanced sampling. And for the income variable, where the Moran index is fairly high, the gains were around 30 to 50%. And then for the labor market participation variables, we were between 25 and 30%, and up to 25% for demographic variables, which are low Moran's index. And then the question is, why do we have this gain? Is it only because of the spatially nature of the spatially balanced, or and this was not clear? Are we using, so the question is, are we using the same auxiliary variable because we are balancing here? So are we comparing with the same auxiliary variables? And if so, what happens if instead of the HT estimator, we use a calibration estimator? My guess, and maybe I'm completely wrong, is my guess that the gains won't be as high, because this is a PPS with HT, is known to be fairly stable if we have a nice relationship. And so here, but if we go to calibration, then maybe we won't see the gains anymore. And I don't know. Okay. But let's assume that we don't see the gains with calibration estimator, because at the end, this is what we're going to use. Then we can ask the question is it worth it to use spatially balanced sampling? Because now we are generating some complexity for the statistical inference, in particular variance estimation. Now it's more complicated when we use spatially balanced sampling, right? Even with balanced sampling, we don't, it's difficult to estimate the variance. And also if we, and this I don't know, but if we do small area estimation and we want to account for the sampling design in the model, now how do we account for a spatially balanced? So does it make the model a little bit more complicated? So, but if at the end we are able to show that the spatially balanced sampling brings some improvement, then sure, then it's worth the complexity. But so this was a question I had. And one advantage of spatially balanced sampling is it's no longer necessary to perform stratification at the sub-provincial level. So we don't have any stratification. But the question is, are spatially balanced sampling robust? And we have this issue when we do PPS sampling, for example, with respect to some X variable. And we know that this design will be very good if you have a very nice relationship that goes through the origin. But as soon as you have a misspecification of the model, then this PPS tends to break down, and stratification brings some robustness. So my question here is, do we have the same, are they robust, this spatially balanced sampling design? I don't know the answer to that. The second paper, which is the third paper, is the paper exploring the use of MNO data. And I think this is probably the first experimentation with MNO data, at least in Italy. And the question here, do MNO data help in building better estimators of predictors of flows? And I'm not familiar with MNO data, but there are some potential issues with MNO data, and for example, measurement errors, right? Location errors. There may be some missing data in MNO data because the devices may be inactive and so on. And there could be also under coverage, because if we are, if we only represents only particular operators. And one of the questions I had, and I don't know, do we know in Italy if MNO, what is the magnitude of these errors in MNO data? I think that would be interesting to see, because then they can explain what will happen when we include these variables in the models. So essentially in the paper, there were two cases. If we had a sample in the domains, so if Nij is greater than 0, then essentially the authors used the eBlob based on Fair-Elliott model. And then when we had empty sample domains, which happens a lot, then we had two options: the customary synthetic estimator and a new approach based on transfer learning. And this transfer learning was based on a proxy variable, IJ star, available from an independent source. From what I understood from the paper, it looks like the authors computed the synthetic estimator based on the 2011 census data and admin data, and also MNO data. So that was used for the synthetic estimator. My question is, did they include also the proxy in computing the synthetic estimator? Because if the proxy is available, then it makes sense to condition on the proxy to compute the synthetic estimator. And if the proxy is very highly correlated to the true flow, then maybe it's going to improve a lot for the estimation, right? And similarly, we can include the proxy in the Fair-Elliott model. So I was not sure if the proxy was included. And if included, what is the contribution in improving the estimates? Now, from the table, so we don't have exactly the same table. This is a bit different, but at the end, the conclusion is the same. When we compare the BIC, it looks like in the presence of the other information, census and so on, the MNO data did not bring much in the model. Okay, and so the question is it because it suffers from potential measurement errors that weaken the relationship with the true flow? I don't know, right? And at the end, for most domains, for most sample domains, the EBLOP was essentially equal to the synthetic estimator. This is a table in the paper where they showed the gamma value, so the combination between the synthetic and the direct estimator. And essentially, those are synthetic estimator, which suggests that the number of domains is large, which at the end makes sense if the domain is large and the sample size within domain is small, and then you will favor the synthetic estimator. But I was surprised that, it was really going towards the synthetic. In fact, the third quartile, if we look at the third quartile, the gamma value, so this combination was 0.03. So essentially, we put all the weight on the synthetic estimator. Because of lack of time, I will skip that. This is the synthetic estimator. So this suggests that the model does not fit this is the relationship between the direct and the synthetic. On average, under the design and the sampling design, they should have the same expectation. So, and this is the line y equal to x. So I'm guessing there is a problem with the model, and maybe some piecewise linear regression would work better than this model. One thing I was also surprised, and maybe the authors can when we look at the direct versus the Fair-Elliott estimate, they look this seems to be the line y is equal to x, and they seem very similar, as if small area estimation doesn't do much with respect to the direct estimator. We would expect when we use the Fair-Elliott model that the estimator are more stable. And in fact, the design expectation under the model and the design of the EBLOP estimator, given the direct estimator, is not equal to the direct estimator. So there is no reason why this point should align on the line y equal x. We would expect to have less variability on the y-axis. Maybe this is what we see here. I don't know, because it's like, and in the second picture, when we have more data, it seems that this is what we see. But I was a bit surprised to see everybody lined on this line. So this is a question also I have. So some final remarks for the paper too. There were some transformation, maybe not mentioned but and I was wondering why the data was transformed. Did the authors find some influential domains? And so in this case, can we apply robust method? Robust small area when it's area level model, it's a bit different from unit level model. But I was wondering. And then because MNO data is complex, I don't know what type of data they are, like the time and the location. Maybe worth to explore the use of machine learning method, and so for area level models such as random forest, and this has been done by people at StatCan very recently, but maybe interesting to do that. And finally, this was maybe not discussed in the paper, but we would need to estimate the mean squared error in the case of spatial model, because there is a spatial component. And I think maybe the good starting point will be Molina and Nicola somewhere, and Monica a paper. Finally, the third paper on accuracy. when we have a multinomial variable. So essentially the setup is we have a finite population, we have S as sample. Assumption is that sampling is non-informative, so I assume that the design variables are incorporated if the model, if they are appropriate. And the survey variable, as Stefano mentioned, has K categories. And the idea is to estimate the domains, the domain totals. And so essentially what we have is that we have Y available for all the sample units, we have X available for all the population units, and essentially the estimate is just we estimate the relationship between Y and X based on the sample, and we apply on the non-sample units. So for the domain, our estimate is just the sum over the domain units of the prediction. So it's essentially a synthetic estimator, right? This is a synthetic estimator. So it's nice features, it's simple, and approximately model unbiased if the first moment of the model is correctly specified. Drawback is vulnerable to bias if model is specified, which is possible. Stefano mentioned unplanned domain. So we have unplanned domain. We have this problem of uncongeniality, right, of Meng. So here you may have a problem of bias. So for planned domain, I was wondering, can we consider, instead of a synthetic type estimator, can we consider a regression type estimator that uses a design, and that so we have a double robustness? Of course, if this sum here is equal to 0, it's called internally bias calibrated, and we're back to the synthetic estimator. But in general, this sum here may not be 0, and so for planned domain, we may have a design consistent estimator. So I understand that at the end, what we want is to provide to the data user some predicted value so that the data user can compute it. So here what we could do is, and this is not the convenient form for this, but I think one possible solution would say to use some kind of calibrated imputation. That is, we manipulate the prediction so that when the data users compute, at least for planned domains, the sum of the prediction, it matches this regression estimator. So we have this double robustness, and we are less vulnerable to model misspecification. So this is as a measure of accuracy, this is the measure of accuracy that the authors propose. So the E lambda is the expectation with respect to the sampling design, and Vy is with respect to the model, essentially. And they have this approximation, and I think the approximation, correct me if I'm wrong, is okay if the sampling fraction is negligible. And I think I worked it out for the ratio, and this is what I found, and which is okay because I think at the end you had a sampling fraction of 5 or 10%, which can be considered negligible. So with this GMSC indicator, we have a variance under the model. So it requires the second moment of the model to be correctly specified. And because we are dealing with a multinomial model, so let's say a binomial, the variance is pi 1 minus pi. So it really depends also on the first moment of the model. So everything depends on the first moment of the model. But if we were using a regression type estimator, maybe we could use something like a design variance without going through the model. Maybe it would bring some robustness. I don't know. Another way to so the paper investigated the use of a parametric model, so which is vulnerable to model misspecification either on the functional form or omission of interaction. And I was wondering if we could, if an alternative method such as this one, where we could use machine learning procedure, so we would predict the Y variable using any machine learning procedure, then use a clustering algorithm to form cells, and then within cells, you use random hot-deck imputation. So this would be robust to model misspecification. And we could do variance estimation. Of course, we will assume that the number of classes are fixed, and made it to some underestimation. But typically, if we do things properly and we do use some cross-fitting procedure, then we should be not too bad. And another question I had, but of course we won't have that, is you showed estimate for the bootstrap, and the bootstrap seems to be very unstable. And I was wondering what kind of bootstrap have you used? Because I would be surprised that it was that unstable. Last thing is that I think in the paper it mentioned that we could take this indicator and extend that to machine learning methods. But if we do, there is a lot of work to do because you have a VY, right? And I think that that's not trivial to do that. So okay, if you have a boosting. So thank you for this is my discussion. Thank you. So we have time for very quick questions. Anybody? The authors? 1 minute. Yeah. Maybe the authors. I don't know.
I will give just short answers to your remarks, your comments. Okay, first of all, as regards the first experimental study, as regards the comments about the two tables and the behavior of the two calibration, of course, we have to go more deeper to analyze these results. The two tables refer to different estimates. The first one refer to the employed estimates. The second one to a generic estimate of a proportion of 15%. But even if the variable is different, we have to check if why the results are different for the second social survey. And as regards the territorial behavior of this sampling scheme, in the experimental study, we made also the analysis at a more detailed territorial level. I didn't present these results. And okay, we checked very many. There are many other results respect to what I presented. And as regards to the second study, calibration is a future extension already planned for the spatial balanced design. And okay, we have to take into account that also for this study, this is not the first one on spatial balanced design, but another bigger than this one has been conducted last year for the population census survey, the master sample, in which both the estimators, in which the Orbis-Thompson estimator has been compared also with the calibration estimator and also with a small area estimator that is currently used for the census. And in this case, the results were the gain of efficiency was not so big as I presented for just at the first stage, but still there was a gain in the efficiency.
Thank you very much for your answer. So I think we have to stop.
Just okay. With reference to the first paper, I would like to add that with reference to small area estimation, one of the characteristics of spatially balanced methods is to fill on to be more to fill on small area domains. So this is an advantage in order to produce direct estimates, basic direct estimate. We could have some empty domains, but this is one important